Initially, our predictions of the orbit are pretty uncertain. There's a long region where it could be. We didn't know its orbital period perfectly, effectively. So it spreads out along a line. That line happens to intersect where the Earth will be in 2040. So the Earth is there. There's this long streak, hundreds of thousands of kilometers long. We say at this point that there's one chance in 500 of it hitting the Earth. But this is just a way of quantifying our ignorance of where exactly it's going to be. The first thing we want to do is go get more data and refine our knowledge of where the object is. So a year later, 2012, got observed again. We now know that in 2040, 2011 AG5 will be over here. The Earth is here, so it'll be a couple times further away than the Moon is from Earth. No risk to anyone. And if we're still doing radar astronomy in 2040, we go plant some cool pictures. Okay. What do we do if we find an impactor? The really small ones, much smaller than Chelyabinsk, we go meteor hunting. In this case, we is Peter Yuniskins at the SETI Institute. Peter is a professional meteor hunter. So he gets to go to the most unusual places in the world if he thinks he can find meteors there. He found some stuff up in Sutter's Mill a few years ago. You may have heard about that one. It was some of the old gold rush areas that had meteors dropped upon them. He also got to go to northern Sudan. In 2008, asteroid 2008 TC3 was discovered. 30 hours later, it flashed in the sky above the Sahara Desert. This caused a certain amount of anxiety for a little while because a bright flash and explosion in the sky above Sudan is a little bit anxiety-provoking for many people. But all it did was drop a bunch of meteorites across this section of the desert. So Peter Yuniskins flew over to Khartoum. Moe Shaddad is a professor at the University of Khartoum, and many of his students organized, and they and Peter hiked back and forth across the desert and picked up a bunch of meteorites. So if any of you ever visit the SETI Institute offices, you can see pieces of this meteorite. Those are the very small objects. Something like the Chelyabinsk impactor, maybe Peter would run towards the explosion because he likes to run towards meteors. I make fun of him about this. Most people would want to stay a significant distance away. Larger impactors, you talk about moving people out of a city if you have a few days to a few weeks of notice. There's a group at FEMA, Leviticus Lewis, been working with, actually integrating what happens if we have to evacuate a city due to impending asteroid impact into disaster planning. Hey, it happened once. Think about this. If we have something like the larger objects, though, a few hundred meters wide, then we talk about asteroid deflection. So again, nothing 1 kilometer across or larger will hit the Earth the next few hundred years. There is a possibility of something a few hundred meters wide. We haven't ruled out all of those potential impacts yet. We haven't found all the objects. And orbits are still uncertain for a large number of them. So how do we move an asteroid if we have to? There are several different ways people have talked about for doing this. 2 of them have gotten the most attention. These are kinetic impact deflection and gravity tractor deflection. Kinetic impact deflection is, in concept, fairly simple. You shove the asteroid out of the way. But how do you move them? Shove.
じゃあ、おお、なんか芝違う。
actually been approved. The asteroid redirect mission was the NASA concept for gravity tractor deflection demonstration. That was canceled a bit over a year ago. But the DART mission is going ahead. NASA missions have a tendency to contrive acronyms. DART is Double Asteroid Redirection Test. This in turn is part of the Asteroid Impact and Deflection Assessment, or AIDA. Those are the mission names. But the concept here is that we'll take a spacecraft and run it into an asteroid and see what happens. Now, the DART project, which is being led by Cheryl Reed over at the Applied Physics Lab right now, the goal is to run into the satellite of a binary asteroid. Because in this case, we have a relatively small asteroid, Didymos Beta, is the official designation for the thing, that's in orbit around a larger asteroid. And if we hit the spacecraft into the asteroid, it gets destroyed on impact, and it shoves both the orbit of these two objects together around the sun, slightly. More importantly, it causes a much larger change to the orbit of the moon around the main asteroid. So we have redundancy in the design. If we can't measure the deflection directly by a monitoring spacecraft or radar ranging, we can observe just the light, we call the light curve of the system. Time when that satellite passes through the asteroid's shadow at particular times, very precisely, and measure even a very small deflection, independently of any instrumentation that might be flown along with the spacecraft. So DART is going forward. You can get information at the web address there. And it is to do this deflection of asteroid Didymos Beta in 2022, if the mission goes ahead. We'll see what happens. I'm just going to finish up by mentioning that there's a lot of other asteroid missions that have happened. I've talked about some of them already, but I didn't realize actually just how many there are until I put this slide together. Despite actually knowing about all the missions, it just struck me as how many there are when I made the list. So there have been 3 asteroid missions in the past to near-Earth objects. The first one was the NEAR Shoemaker spacecraft, which landed on the asteroid Eros after mapping the whole place back in the 1990s through to the very early 2000s. 2005, the Hayabusa spacecraft got to the asteroid Itokawa. This is the other side of Itokawa from what I showed you before. And then in 2012, the Chang'e 2 spacecraft flew by the asteroid Toutatis. Chang'e 2 is part of the Chinese Space Agency's lunar exploration program. It was initially orbiting the moon. They played some fun orbital mechanics tricks to fly it out of Earth-Moon space and arrange it to pass very, very close to the asteroid Toutatis, less than 1 kilometer from the surface, actually, which is a little bit closer than they had intended. So I'm glad the radar predictions of where the asteroid was and how it was arranged in space were correct. If I was giving this talk a month from now, I might be showing you pictures from Hayabusa 2, which is currently on a final approach to the asteroid Ryugu. It's closer to the asteroid than we are to the moon right now. Makoto Yoshikawa's team is doing very good work there, and ideally we'll have a lot of data soon. But right now, it's just a dot on the spacecraft's cameras. The OSIRIS-REx spacecraft is on its way to the asteroid Bennu, which we have radar observations of, so we can make a computer rendering of it. But we don't have actual pictures yet. Those will come in August of this year. Bennu has a series of potential Earth impacts between 2175 and about 2200. The impact probability you may see assessed as 1 in 3700 or so right now. Again, that's just a way of quantifying our uncertainty in where the asteroid will be. OSIRIS-REx will provide extraordinarily accurate measurements of where Bennu is in space and how fast it's moving, better than we can get from the ground. And it will do that for several years until it leaves the asteroid to come back to the Earth, a few years. And that should help resolve the ambiguity in where Bennu will be at the end of the 2100s. And ideally, it'll rule out the impacts, or it may rule out some of them and not all of them. We'll see what happens. I talked about AIDA in DART. That will actually visit another asteroid, 2001 CB21. It just happens to be able to fly by it on its way to Didymos. And then there's other projects. NEA Scout is a small satellite project by Julie Castillo-Roguez down at JPL. Destiny is another small satellite project by Tomoko Are in Japan. That's to go to the asteroid Phaethon. Phaethon is kind of fun. It gets very, very, very close to the Sun, closer to the Sun than Mercury. So it actually heats up to the point that not only do we have Yarkovsky effect pushing it around, the heat stress actually causes dust grains to crack and fly off the surface. So it causes a meteor shower on Earth every year. No hazard to the Earth anytime soon, but it does create a nice light show. And then there's a proposed Chinese asteroid mission that would go to a couple of other asteroids, including an asteroid called Apophis. Apophis keeps getting featured in discussions of the impact hazard because it very briefly was assessed as having a few % chance of hitting the Earth in 2029. This was back in 2004. It very quickly became clear that it will not hit the Earth in 2029. It will, however, come extraordinarily close to the Earth. So if anybody wants to travel to Brazil, you can see it fly by with their naked eyes overhead in 2029, if you want to make travel plans. All right, so I have talked about a lot of stuff, and I think I'll finish up here, and I'll switch over to questions. Thank you again.
On the Yarkovsky effect, if you had an asteroid that was uniform on the surface and reflection and perfectly spherical, wouldn't the effect of light from the sun would be to add energy to the asteroid's orbit without necessarily giving it more spin, so that it would actually get into an elliptical orbit over time?
So there's actually a couple of effects here. There's direct radiation pressure from the sun, sunlight coming in. That itself has momentum. Then there's the Yarkovsky effects of thermal re-radiation, heat going back out.
Oh, yeah, I actually meant to also say the asteroid wasn't spinning. So if it was spherical and not spinning and uniform in its reflection,
if it was completely, magically, completely still and not spinning, then you just have solar radiation pressure, and that does change the eccentricity of the orbit.
Right.
So it's the Yarkovsky acceleration, but the main effect of Yarkovsky in the short term is to change the semi-major axis.
Yeah, although even in an asteroid that's spinning, some of the light is instantly reflected.
And you have to correct for both reflected sunlight and re-radiated heat.
Yeah, okay.
Every year we seem to go through a cloud of meteorites. Why doesn't that just suck into the gravity of the sun? Why does it sit out there?
So if something's in orbit around the sun, absent some other force changing that orbit, it will stay on that orbit. So if we have something like Phaethon, which is occasionally spewing out dust particles that become meteors, they stay on nearly the same orbit. They tend to spread out a little bit because of things like radiation pressure. And typically the first effect is to spread them out along the orbit. So we get a long string of dust particles sharing the orbit of Phaethon, or whichever other comet or asteroid, and that forms a ring around the orbit, and then the Earth can run through that cloud. It also spreads out around the orbit so that it may be hundreds of thousands, million kilometers wide, and the Earth runs through that over the course of a day, and we see those flashes for however many hours.
So it is in orbit?
Yes. And unless the eccentricity changes to the point that it falls into the sun or it gets too close that it vaporizes, it stays in orbit.
Yes, so late last year there was this cigar-shaped near-Earth asteroid that got a lot of publicity through NASA, et cetera, on the news, and I was just curious if you could comment on that, if you knew what I was referring to, and if anybody else knows what I'm referring to. Is the object
Oumuamua?
If anybody...
Okay, so Oumuamua is not actually a near-Earth asteroid.
Okay.
It passed near the Earth, but Oumuamua is something far stranger. It's an interstellar asteroid.
Strange? Yeah.
So this came into our solar system from the outside. We haven't actually seen that happen before. We've seen asteroids and comets get kicked out of our solar system. Their eccentricity takes them out to the orbit of Jupiter. They fly by Jupiter. They can get just enough energy. They fly out of the solar system and keep on going, like the Voyager spacecraft and New Horizons have done. And they never come back. We expected that should happen around other stars, giant planets, particularly double star systems. You can do this more efficiently, maybe. We had never seen one before. Oumuamua was discovered actually after it made its closest approach to the Earth and when it was on its way back out. But it became clear it's traveling very, very, very fast. So fast that it could never have been gravitationally bound to the sun in the first place.
So I was wondering if you can talk about the practicality of maybe using some of the effects you were talking about for either blocking out or perhaps focusing sunlight to deflect potentially dangerous asteroids.
So people have talked. The question is using Yarkovsky effect to move asteroids around?
Yes.
This has been suggested, but it's very, very, very slow. So somebody worked out, I think, if you were to take a container of powdered aluminum, which is very reflective, and you were to coat one side of 1950 DA, this asteroid I mentioned that has the potential impact in 800 years, you could change the outcome of that, impact, not impact, by 10,000 kilometers over 800 years. That's really slow. And we prefer to do the deflection faster than that, if we can. So the gravity tractor deflection and the kinetic impactor deflection, much more rapid.
Earlier, you mentioned what might happen to a person on the surface of an asteroid. I was wondering if you could expand on that, and if there's a kind of relatable analogy or metaphor that would capture that experience, something along the lines of maybe loose snow.
I'm not sure about this because, again, our normal physical intuitions tend to break down. So NASA has discussed sending humans to near-Earth asteroids or bringing pieces of asteroids in space to astronauts who are in space. One of the uncertainties was what happens when you grab the surface. I talked about how you can have electrostatic charge buildup. You might end up with some massive dust bunny-like thing where the astronaut touches the surface and now their hands are coated in electrostatically stuck dust clumps and they can't move their gloves anymore. That would be really uncomfortable for everyone. But I don't know what a good analogy to that is. Maybe a dust bunny is the best thing I can come up with.
Okay, I'm worried about this asteroid may hit in 800 years. What's the exact date, and particularly how big is it?
I'm sorry?
What is the exact date of that asteroid may hit in 800 years, and how big is it?
I'm recalling that it's March 16th, but I'd have to look it up.
How big is it?
It's about it's a little over 1 kilometer across.
Ah, okay. And that would do how much damage?
If you go online, you can Google 1950 DA tsunami. You can see a series of simulations of what happens if you drop it in the middle of the Atlantic. I can't actually tell you where on Earth it would land.
Yeah.
Because we can plot this line where the asteroid can be. We can plot that line onto the Earth, but I don't know how the Earth will be oriented in space at that point because the length of the day is uncertain.
And what's its chance of hitting us? Is it
it's about 1% in the current assessment.
1%? Less than 1%?
We're not sure if it's somewhere of that order. Maybe we're quantifying our ignorance here. Ideally, we'll rule it out completely, and this won't be a problem anymore.
All right.
But we need more data.
I'm hoping for tax day. So, even at these low densities, why would you not just land a rocket object, or a rocket on it with perhaps a dish-sized contact plate, if you will? Or why would you not just push it?
It is a pile of rubble, and you put a rocket engine, press it into the surface, it's not clear how it reacts. So I mentioned the asteroid redirect mission, which was a NASA proposal. The idea there was to pick up a block from the surface of a near-Earth asteroid, something that might probably fit on this stage, and bring that back to Earth. One of the big engineering challenges there was how do you design a system to grab on to a large block that's several tens of tons and move it around space in a controlled way with a rocket. Moving around the entire rubble pile as opposed to a block that has a certain degree of cohesion, that becomes much more difficult. The gravity tractor has the advantage that it just pulls everything uniformly. Was there a question here?
I was wondering if you have to destroy the satellite.
So I
Like
talked
when
about
deflecting.
how we have to, this is for the kinetic impact deflection, why it has to get destroyed on impact.
Yeah.
So I talked about how we need as much momentum as possible. Momentum is the
Yeah.
product of mass and velocity.